So what do we remember about limits? I remember something about how derivatives came from limits, but then that's about it because the rest of the course is all about derivatives. So let's go back and review a little bit about limits. When you are evaluating a limit, we had these four strategies. We talked about different strategies or different tools. You got to pick the right tool for the right job. There's one other thing to consider. Does anybody, any chance somebody remembers what it is before you even start with these tools? Yeah, what do we mean by substitution? Not that substitution, but what do we mean by substitution? Yeah, so can I just sub 0 in and will it work? If I sub 0 in, I get negative 64, third root of that is negative 4, plus 4 is 0 over 0, so it's indeterminate, right? 0 over 0 means there's a hole, which means the limit may exist. If we think back to the definition of limits, you've got left-hand limits. So as x approaches a value, it doesn't have to be 0, it could be anything. As x approaches a value, what does the function approach from the left? What does the function approach from the right? And we did all these different things where we had, a graph that's just like this. It's continuous everywhere, so it's fine. Or we had a graph that might have been like this. And so it has a left-hand limit, it has a right-hand limit, but the limits are not equal. So it doesn't have a limit overall at that value. It would have limits at other values, but not at that value where there's a break in the graph in this case, right? So that's what limits was all about. So we do that quick check, subbing in the value that x approaches and see what it works out to. And if it's 0 over 0, then we have these four main strategies that we would use to try to work it out. So in this case, which one of those four do we want to use? Substitution. I want to substitute and get rid of this fraction exponent. So I'm going to let a equal x minus 64 to the 1/3. There's 3 mini steps to this. That's the first step. Step 2 is solve it for x. So I cube both sides and then add 64. So I have something to sub in at the top and something to sub in at the bottom, so I can get rid of all the x's. And then the third step is this. I have to figure out as x approaches 0, what does a approach? Negative 4. How do you figure that out? I would sub it into that top line. So sub 0 in for x and calculate a. Okay? Now I have all the details I need to go ahead and substitute and continue to solve. So we change the limit statement. As a approaches negative 4, x minus 64 to the 1/3 can be replaced with a. And x can be replaced with a cubed plus 64. And if you've done it correctly, every time the part of this that makes that gives you the hole in the graph, the 0 over 0, that factor, you'll get it on the top and the bottom, and it'll factor out. And we'll have a leftover function that we can actually sub into and solve. That's what happens every single time. So I still have some work to do here. One of the other tools, which is going to be factoring, because I have a sum of cubes on the bottom. And there's the a plus 4 factor. That's the part that gives me the 0 over 0. Because a is approaching negative 4 now. Of 1 over a squared minus 4a plus 16. And now I can sub in. Remember this? A little bit? Okay, stop me if there's any questions. We'll keep going. Next one. What are we going to use? Which of our 4 tools will we use for this one? This one should be obvious. If there's big fractions in it, we're going to use the, what did we call it? What did we call it? Oh yeah, both. Fraction over fraction or common denominator. There's sort of 2 ways to approach this. I think it comes up again in this review, so we'll do it once one way and once the other way maybe. So I'm going to multiply this whole thing by, oh, and this is supposed to be plus. This is supposed to be x plus 3. Otherwise, it doesn't work out to 0 over 0. We forgot to check that. But that's because I already checked it, so I know. But we're supposed to check it first, right? So plug in 3 and make sure that you get 0 over 0. I obviously get 0 on the bottom. I get 12 over 6, that's 2. And then 6 over 3, that's 2. So 2 minus 2 on top is 0. So it's 0 over 0. So it does work out. But there's a little typo in there. It's supposed to be x plus 3. Okay, so I multiply by 3 times x plus 3 over 3 times x plus 3. And whether you do it this way or the common denominator way, it's like after 2 steps, they look the same anyway. So it's up to you, whatever is your favorite. So when I multiply 3 times x plus 3 by the first part of the numerator there, the x plus 3's are gone. So I just multiply 4x by 3 and I get 12x. Maybe I should write that out. So this was 4x times 3. Minus 2x, and so the 3's divide, and I get x plus 3 over x minus 3 times 3 times x plus 3. I don't want to expand that. It looks like something's going on there with the x minus 3 and the x plus 3. That's kind of just a fluke. But I don't want to expand that because I'm trying to get everything factored to see, to pull the factors out, to simplify this thing. So I'm leaving it in factored form. If it wasn't in full factored form, then you would factor it, but usually the denominator of these guys is. Okay, now we can expand this a little bit on top, because I do have to expand this before I can factor, so I get 12x minus 2x squared minus 6x. Is that right? Yes. Over 3 minus 3 x plus 3. So I get negative 2x squared plus 6x. And hopefully at this point we see where this is going. I factor out a negative 2x on the top, and I end up with x minus 3. You remember this stuff is all nice. There's all these little tips along the way that you're doing it right. Like if you get to this step and it factors out with the 3 over here, right? This whatever this is, that's got to be the thing that factors out. The thing that goes to 0 over 0 with that. So we know it's going to be an x minus 3 term. Like we know that's going to work out on the top and the bottom. It has to. If it doesn't, it's not like, oh, this must be a special case. No, you made a mistake. You're doing something wrong. Okay? It's funny all the things we tell us in the moment of writing a test where we start to like second guess things and come up with who knows what. And now I can just sub in. I'm going to do it over here because I just ran out of room. So this is negative 6 over 3 times 6. So the 6's are gone, and I got negative 1 over 3. And the last one of these, which type is this going to be? Again, it's pretty obvious probably at this point. We're going to conjugate it. Again, you check that the negative 3 subbing in gives you, but you get square root of 16 minus square root of 16, and you get 0 on top, obviously, so it does work out that way. So I multiply by the conjugate. What's the conjugate? Remember, you always have to multiply by 1. Some people get confused, and especially if there was a radical on top there, some people get confused and they do the conjugate of the top over the conjugate of the bottom or something like that. Like they do x minus 3 over this. But you can't do that because then you're multiplying by some other thing, not 1. As long as we multiply by the same thing over the same thing, we're multiplying by 1. We're not changing it. But the conjugate means I multiply, you just change the sign. Is this familiar? We're not going too fast here. We kind of remember what's happening. I don't have all day to reteach this from scratch, obviously. So again, on top, I'm not going to expand it. It's not really going to be worthwhile to expand. So I'm going to just leave it as x plus 3 times all these 2 square roots, right? Like that. And on the bottom, we want to know how the impact of the conjugate, the whole point of this. You got the plus and the minus, so the middle term's gone. So it's just the first term squared minus the second term squared. And because it's square roots, that's what makes it kind of nice. So it's the first term, which is 4 minus 4x, minus the second term, which is x plus 19. That's what it should work out to on the bottom. So I've got negative 4x minus x is negative 5x, and 4 minus 19 is negative 15. Boy, that worked out nicely. Isn't it beautiful how it always works out? You're like, wow, there's an x plus 3 factor in there. You always want to write that last one with the factor gone with the limit statement before you sub in. That's like a key step that we're looking for. Negative 4 times negative 3 is 12. 4 plus 12 is 16. Square root of 16 is 4. Negative 3 plus 19 is 16. Square root of 16 is 4. So 4 plus 4 is 8. So this is negative 8 over 5. Feel good about that? Use definition of a limit. Ooh, this is like where you're not allowed to take the derivative using our fancy new derivative tricks, right? We learned about derivatives in Unit 2. Well, we might have learned about the word derivative in Unit 1, but we learned about how to like take derivatives of polynomial functions and the quotient rule in Unit 2. We didn't know how to do it here. And you're very likely to be tested on both those things. Certainly there's going to be derivatives on it. But the definition of a derivative. This is where we developed the tricks. Okay? And so when it says this, first of all, there's a couple of key things in here. It says definition of a limit. So what does that mean? Thank you. And it says determine an expression. Where did my photocopies go? Oh, it is this. Determine an expression. So we can't sub in 5 early on. That sometimes makes it easier. We're not allowed to do that. So there's sort of 2 ways we can do it, and hopefully we have time, so we're going to try them both. So the limit, we're going to do this one first. As x approaches a of f at x minus f at a over x minus a. This is one of the ways that we can do it. And on the exam, you'd get to choose your favorite. Method 1 or method 2. Probably the substitution step is, like this step coming up is the most important one, that if you can get this step, you can probably work out the rest. Okay, but this is where some people have trouble visualizing what it means. F at x. So this is the function f. So f at x is just that function. So I start with 5x over x plus 5 minus f at a. So now this is like f at some value a, and I replace x in the original function with a. So this is now 5a over a plus 5, all over x minus a. Okay, so in this case, I'm going to do a common denominator on top. So this is like, or you could do the fraction over fraction like we did in the last one. Okay. Trade you. There you go. So a common denominator is like I'm multiplying numerators by the other denominator. So this is going to be 5x times a plus 5 minus 5a times x plus 5 all over the common denominator that I just created. And then this is going to be times 1 over x minus a, or you could do it like this, that whole thing over x minus a. Those two things mean the same thing, right? Are you okay with that? Yes? Yes, yes, yes. But I'm doing it like this because then I see that the x minus a gets grouped with these two, so they're all on the bottom anyway. So I'm going to expand the top. 5ax plus 25x minus 5ax minus 25a over x minus a, x plus 5, a plus 5. Start cleaning things up. Five ax minus 5ax gone. I get 25x minus 25a. Very nice. Now I can sub in the value that x is approaching, so I sub in a. And I get a plus 5 times a plus 5, so a plus 5 squared. Just looking at the original function, if I use the quotient rule, derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. You got that bottom squared part. As long as the top part works out to 25, it's the same thing, right? But I see the bottom squared there. So like kind of fits, kind of makes sense. And then we were supposed to find it at x equals 5, or in this case, a equals 5. So then this is equal to 25 over 5 plus 5 squared, which is 10 squared. So 25 over 100, which is 1 over 4. So that was one of the methods. Is everybody okay with that? This is the other one. This is what I mean, pick your favorite. And when you're practicing, go with the one that you like better. X approaches a or h approaches 0. Which one do you like better? So this is f at x plus h minus f at x all over h. If you were going to be taking anything like this in university, I would imagine you would have to know both. Unless you were taking a proofs course. Like if you were taking Calc 1 or Calc 2, I don't know that there would be... They start to do these things called epsilon delta proofs, which is a little bit different. So, I don't know. Anyway, but I think you'd have to be familiar with both. But for this exam coming up, you only have to know one. All right, so let's see how it looks different. I think they work out to be about the same number of steps. The substitution's a little bit harder. So I have to substitute x plus h into the original function. So it was 5x, so it's 5x plus h over x plus 5, so it's x plus h plus 5 minus f at x all over h. Again, I'm going to do a common denominator, so I get 5x plus h x plus 5 minus 5x times 8x plus h plus 5 all over h times x plus h plus 5 times x plus 5. Don't forget that limit statement. Don't make that mistake. That's an MHF mistake where people write the limit as h approaches 0 equals, they put the equal sign there. No, 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 no. That's definitely, don't do that. Don't ever put the equal sign after the limit statement. That doesn't make any sense. The limit statement is part of the expression that you're saying. That's equal from line to line. Okay, so I'm going to expand this, and it works out to something like this. 5x squared plus 25x. You're going to have to take my word for it. Plus 5hx plus 25h minus 5x squared minus 5xh minus 25x. All right, and a whole bunch of things here better cancel out. 5x squared minus 5x squared. 5xh minus 5xh. 25x minus 25x. So I'm left with 25h over h x plus h plus 5 x plus 5. And this is what we're looking for if you're using this form, this version. Every term on the top should have an h. We only have one and it has an h, so we're fine, but often remember there's like binomial or trinomial or something on top, but every term has an h, so we common factor out the h to the front. But in this case, I could, and it's just got to go away with that. That's my 0 over 0. So this part's a little bit easier if you use the h approaches 0 version. It's a little bit easier later on, a little bit harder at first. The x minus a is a little bit easier at first, a little harder later on maybe. I don't know. I don't know that one's easier or harder. It's really preferential. So, oh, didn't mean to do that. Now I can sub 0 in, and I get equals 25. So 0 in for h. I get x plus 5 all squared. So I get 1 over 4 again. When I look at it like that, the h approaches 0, 1 looks shorter, but it might be because I wrote the lines a little bit smaller. And I did some of the expansion in one step. It might have taken us 2 steps if we were doing it, especially on an exam, you know, and you're taking your time. So, I don't know. Up to you. What do you think about that? That is Unit 1 in a nutshell. Exciting? Unit 2, we'll do a couple of units a day, 2 or 3 units a day. We'll try to get through at least 2.5 units today, I think. That doesn't make any sense. Given that y and u below, redacted. Given y and u below, find dy by dx at the point where x equals 1. I could sub u, which is this whole big mess, in for u. And take the whole derivative in place. But it would be nasty. So we have this beautiful notation, Leibniz's notation, that allows me to do this. dy by dx. So if I take the derivative of the first one with respect to u, I'm going to get dy by du. And if I take this second one with the derivative of u with respect to x, I'm going to get du by dx. So dy by dx will just be the product of those two things. Whoops. It literally is like fraction math where the du's cancel, and I'm left with dy by dx. So I think we should do that one. Oh, I might not have one for that actually. So dy by du, quotient rule, the derivative of the top with respect to u is just -1, right? So -1, you don't have to show it that way, but it reminds us that we actually did something there, times u plus 1, minus the derivative of the bottom, which is 1, times the top, over the bottom squared. Whoops, x, where'd that come from? I'm going to clean this up a little bit, and I get negative u plus u, so those are gone, and I get -1 minus 5, so I get -6 on top, u plus 1 squared. Du by dx this is the sum of two things, so I just take the sum of their derivatives. I just take their derivatives separately. So I'm going to do the derivative of this first bracket, take the exponent, multiply by the outside, so this is 1 over 2 times x plus 3, subtract 1 from the exponent, so it's to the -1 over 2. I'm going to do the same thing with the second part. That's x to the -1. So I multiply by, right, this is x to the -1. Send tight. So I'm going to multiply by -1, 6x to the -2. Which equals 1 over 2 root x plus 3 minus 6 over x squared. Yes? No, we don't have to do it first. Why would we do it first? Yeah, sure. That's, again, preferential thing, right? I don't have to do it first. But absolutely, I get to this point and I'm like, ugh, what do I do now? Well, so if you didn't remember this type of question, you might not be sure what the rules are. There's no real rules. I don't have to come up with an expression just in terms of x. I mean, I could replace the u with my expression for u, and I'm just subbing in x anyway, but I wouldn't bother. I would leave it as u, and then what we're going to realize is if x equals 1, then u equals 1 plus 3, the square root of 1 plus 3, plus 6 over 1. So that's 2 plus 6, which is 8. So if x is 1, u is 8. And now I can sub in here. I get negative 6 over 81 times a quarter minus 6, which works out to negative 23 over 4, which works out to 23 over 54. Yep. Oh, yeah, it does look like 12. 1 squared. There, that's better. We good with that? There is a section of the exam that says take the derivative first line only. And then there's another section that's going to say differentiate and simplify fully. So we'll see what both those look like. Let's go back to basics. When I look at y, when I look at my function that I'm taking the derivative of, it's a product rule because I've got a p and a q. But then each of those things has like a chain rule part where I've got an exponent and I got a bunch of junk going on inside the bracket. So to make my life easier, to organize my work, organize my thoughts, break it down, instead of doing it all in line, this is like making it easier on your brain, your working memory. You don't have to think about as much all at once. I can do this. Off to the side, find the derivative of p. So I bring the 2 down. This is p here, right? So I bring the 2 down, multiply by 4, and then the inside doesn't change, and that's to the 1, and now I multiply by the derivative of what's inside. And I'm going to simplify it. Go ahead and try Q. Don't forget the squared on the bracket there. That's going to actually make a big difference in the end. And then just remember, you don't have to obviously write this down, but if f equals pq, then f prime equals the derivative of the first times the second plus the derivative of the second times the first. Addition and multiplication don't matter. Order of addition and multiplication don't matter. So, I mean, if you mix up those orders, it won't make a difference to the final outcome, but you got to have those combinations. So, the derivative of the first thing is, now this is easy because I see what I mean. I can just focus on getting the parts written down properly. Times q, which is x squared plus 3 all cubed, plus the derivative of the second thing, which is 6x x squared plus 3 all squared, times the first thing, 4x squared minus 3 all squared. We've already done the derivative, so while I'm writing it out, I'm not thinking about and trying to figure them out as I go. And then what is the simplify fully part of this? When it's just polynomials, you're basically common factoring these two things. Common factor the first big pile of junk there and the second big pile of junk. So I'm looking at the monomials out front, 16x and 6x. There's a 2x in common. Now I'm looking at the 4x squared minus 3 bracket, and I can factor one of those out of each. Now I'm looking at the x squared plus 3 bracket. And I can factor 2 out of each of those. And this is where practicing this a few times really helps, because it becomes familiar, and you sort of, once you get to this stage, they all kind of work out the same. And once you see that pattern, for 1, you confirm that you're doing it right, but for 2, you know, you have that confidence. Okay, so 16x divided by 2x is 8. Those are gone, so I'm left with one of these brackets plus 3 times one of those brackets. Not done yet. And just to be perfect, there's a common factor in that last bracket. So I can pull that out and stick it with the monomial in front. Four x squared minus 3 and 4x squared plus 3. That's interesting. I didn't notice that before. I'm not going to expand that, but that's just interesting. What if that worked out to 4x squared minus 3? Then I could even simplify it further. But anyway, any questions about this? Here's an actual question I want to ask you. Why would I want to do this? Like, why is being able to simplify fully important? Like what? When we did all this work, there was something coming up in the course. Second derivative, absolutely. What else? What did we end up doing with derivatives? So when I want to find the critical values, I want to know where the derivative is equal to 0 or does not exist. So if it's a fraction, I want the top and bottom to be factored so I can see where the zeros are. If it's a polynomial, I still want it to be factored. I can see where the zeros are. If we're solving a word problem, so that's for sketching critical values. If I'm solving a word problem, the maxes and mins still occur where the derivative is equal to 0. So like getting it into factored form like this, simplifying fully, allows us to do all the things that we often do with derivatives, which is set it equal to 0. Okay? So, makes sense. But it's a lot of extra work. And some things we can't do it very nicely with. So that's why on all those tests, there was also always a part, just do a first line derivative. Because some of those things, you couldn't really get it to this form where it could be solved nicely. That was the second question on the page. Okay, does that make sense? Very nice. Keep going. 10 minutes left. We're not going to get through as much as I hoped. Oh, this one's short. Find the points on the curve below where the tangent line is parallel to that line. There's all kinds of different ways this could be asked. We didn't do any implicit differentiation. Is that coming? I feel like it's coming somewhere. Oh, yeah, it is way down the road, isn't it? Yeah, there's one. And that will be one. Okay, anyway. It could just give you the slope. It could say where the tangent line, where it's the horizontal tangent line, or the slope of the tangent is 0. Like it could ask all those ways, but in this case it says parallel to this line. Parallel lines means same slope. So if I can find the slope of this line, then I know what I'm working towards. Otherwise, that line is not relevant. This line doesn't help me in any way, right? So if I go 4x plus 1 equals y, I've got it in an mx plus b form. And so my slope is 4. That's all I need that line for. I want the slope. I want to find the points on this curve where the slope of the tangent is 4. So what do I need to do? I need to find an expression for the slope of the tangent first. That means take the derivative. Derivative of a constant is 0, so that's gone. 7's gone. Derivative of negative 8x is negative 8. And the derivative of negative 12 over x, change the sign, because that's x to the negative 1. And then it's going to be 12x to the negative 2, so it's actually 12 over x squared. That's a good trick. If you just have like 12 over x, the derivative is change the sign over x squared, right? Comes up often enough that if you know that one, save yourself a little bit of work. Okay, so this means I want y prime to equal 4. So I get 4 equals negative 8 plus 12 over x squared. I'm going to bring the negative 8 over, and I get 12 equals 12 over x squared. Multiply both sides by x squared. X squared equals 1. X equals plus or minus 1. Don't forget the plus or minus. And it said find the points. It didn't say find the x values. I found the x values, but it said find the points. So at x equals negative 1, y equals 7 minus 8 times negative 1 minus 12 over negative 1. I think that works out to 27. And I think this one works out to negative 13. Therefore, the points are negative 1, 27, and 1, negative 13. Any questions? I'm going to stop there. We only have 5 minutes. I don't think we have time to get into the next one. It's kind of a longer one anyway, so we'll start that tomorrow.